No, I put that on there so you guys could get extra points easily.
I didn't see it until like last minute. Yeah, it was 30 seconds left and I started it. And I was like, oh my God, what is this?
So did you have enough time to do number one?
Yeah,
Okay. But it wasn't too bad, right?
no.
Okay, good. Did you figure out what coordinate system it is?
Yeah.
Very nice.
Elliptic.
Elliptic cylindrical, yeah.
Can we like schedule it on Thursday instead of Tuesday? If everybody is.
Let me check the schedule and make sure that that doesn't mess up the following homework. Because we already pushed that one back, so that's what I'm worried about.
Sorry.
We already pushed that one back a little, so the only thing I'm worried about is the other homework getting run up, or the other due date encroaching.
Yeah, it's on Canvas. Due date is next Tuesday. It's Tuesday. Yeah. Yeah, we're still recovering from the midterm.
So it's not unless you're probably Tuesday.
All right, let's see here. Right. Oops. How's it going? All right. Was everybody here for the exam? Was it a lot here? All right, let's go ahead and get started, guys. So as a reminder, great. As a reminder, you had your midterm on Tuesday, so hopefully it wasn't too bad. It should have been one question, kind of straightforward. I gave you a big clue that it was going to be on generalized coordinates. So you had to do some of the things that we learned in lecture 1 and 2 and 3, but in the generalized coordinate frame. So hopefully that wasn't too bad. And then there was a question on there, number 2, to allow you guys to sort of offset the points. A really easy question to bias the grade. so that you just write out your opinion, you get full credit, and then that would help you skew your score on number one, right? Okay, good. So this is a reminder that the next class we have is from 8 a.m. to 9:15, and it's in Torg 1030 across the hall. Do not forget, the next lecture is across the hall and it starts at 8 a.m. And homework number 4 at this point is due on Tuesday, so get to work on that, all right? I don't know when we had, okay, I don't know when we had the next homework. I think it's going to come out on the 18th. So I'll take a look, but get it done
Is
before.
homework due at class or is it due at midnight?
It's due normally at the start of class, so you have to turn it in on the morning of. Okay, so not at 8, it'll be due at 9:30, our normal class time in the morning.
Would it be possible to add some extra office hours? Because it wasn't assigned until after the last one.
Yes, let's see. All right, good point. Yeah, why don't you come by either today or we can do another hour on Monday. Email me on Monday if you want. Yeah, if you have any questions, just email me on the homework. We can start another office hour anytime. But for now it's still due on Tuesday, right? Okay, good. All right, don't forget, next class, 8 a.m. All right. So good. Hopefully you guys are happy after the midterm and you're ready to get back into it. So let's do a quick review of what we did before. We're studying waves in anisotropic media which has permittivity, which depends on direction. Could be X, Y, and Z, but we know that in general, we can measure these permittivities in different directions, and we might get a full matrix like this. There are 9 entries, but only 6 are independent based on the Hermitian property of lossless media, right? Lossless reciprocal media. Okay. Then we said if we have any matrix, we can use the principles of linear algebra to do a diagonalization of that matrix. In the process of diagonalization, we obtain 2 vectors of eigenvectors, P inverse and P. I guess it's the same matrix, right? It's a matrix of eigenvectors. There are 3 of them in this case, and those 3 eigenvectors form what's called the principal coordinate system. If you describe your permittivity tensor in the principal coordinate system, it becomes diagonal. It makes everything easy, all right? So what you need to do is find your principal coordinate system, right? And then start working your problem in that coordinate system. All right. Then we looked at a quick example of doing the diagonalization. This is nothing but linear algebra. We had some KDB crystal, which is an actual example, has a permittivity tensor like that. And then we set the first, the determinant of it equal to 0 in order to find the eigenvalues. And then from the eigenvalues, we were able to find the eigenvectors. The eigenvectors represented our new coordinate system, right? And we saw that it was just a rotation about the x-axis. Now that we have a diagonal, I guess it's not restricted to diagonal, but it's much easier in diagonal form. We can represent our permittivity tensor as a ellipsoid. It's called a quadric surface or quadric representation. We have xi, xj, summing over I and j, epsilon I and j, right? We can draw a geometric surface. This geometric surface allows us to construct geometric solutions to wave propagation in anisotropic media. What is the difficulty, or what is the main part of the problem of solving wave propagation in anisotropic media is to find the 2 normal modes, right? There are 2 modes with index of refraction in particular directions through the medium that travel without their polarization changing. And these are very important because they serve as bases or eigenmodes that you can express other directions of propagation in terms of. So there are 3 types of crystals: biaxial, uniaxial, and isotropic. If all 3 principal indices are equal, then the medium is isotropic. That means that any direction you look, you get the same permittivity. It's isotropic. If 2 of them are different, or sorry, if all 3 are different, you get biaxial media. And if only 1 is different, you get uniaxial media. We'll understand the concept of optic axis later on, but if you solve the dispersion relation, you end up with this 2 sheets in the solution. Those 2 sheets intersect at some point. In uniaxial media, they intersect only at 2 points. And you can draw a line through the origin in those 2 points, and that becomes the optic axis. Along the optic axis, you get the ordinary index of refraction, and then along other directions, you can get an extraordinary index of refraction. In biaxial media, the 2 sheets intersect at 2 points, or 4 points rather, and you can draw a line through those 4 points, two lines to those 4 points, and those are two axes or biaxial media. So the index ellipsoid, if we, okay, so we define the electric impermeability tensor, which is nothing but the inverse of the permittivity tensor, right? Impermeability tensor is the inverse of the permittivity tensor scaled by epsilon naught. And from there, we can do the index ellipsoid representation again, but in this case, it's called the index ellipsoid, the quadratic representation again. But in this case, it's the index ellipsoid. Index ellipsoid is very important. So we take the impermeability tensor and we represent it as a surface. It ends up being an ellipsoid like this, especially when it's diagonal, it's aligned with the axes. And we have the index of refraction along the half major axis and half minor axes, right? Okay, good. So we then looked at what are the normal modes. We wanted to define what are these two special directions that through a uniaxial medium, for example, or an anisotropic medium, where we get modes that travel without changing their polarization. All right. So if you have a plane wave traveling along, say, the z direction, linearly polarized in the y direction, it travels with a particular phase velocity depending on the direction of polarization. So here we have traveling in the z direction, polarized in the y direction, it sees a different index of refraction than a wave traveling in the z direction, which is polarized in the x direction. So these two waves travel with different phase velocities because they have different index of refraction in those directions of polarization, right? When two waves travel with different phase velocities, they fall in and out of positive or constructive and destructive interference. And as a result, you can convert linear polarization to elliptical polarization in general in a medium. So the state of polarization changes, right? It goes from linear to elliptical. It could be also circular. Having defined that, we can then say, well, we can construct wave plates, right? So we have some wave plate, which is a particular thickness. So the X polarized plane wave has a different index of refraction than the Y polarized plane wave. Therefore, it travels at a different velocity and it incurs a different amount of phase delay traveling through some medium of a given thickness. So we can design that thickness such that that difference in phase for the two polarization or the two components is exactly 90 degrees. And in doing that, we can convert linear polarized light into circularly polarized light because the conditions for CP are equal amplitude. So we come in with a plane wave, which is linearly polarized at a 45-degree angle that ensures that we have equal amplitude. And then we incur a 90-degree phase difference between the two components by having the wave traveling through a quarter wave plate, a medium with sufficient thickness. I think you'll design one of these in your homework. All right. So what about an arbitrary direction now? We have our index ellipsoid here in x1, x2, x3 space. We know that the primary index of refractions are along the half major axes, N1, N2, and N3. But now we're traveling in some arbitrary direction defined as U hat. That arbitrary direction, so the direction of propagation is U hat. We draw a plane orthogonal and through the origin of that vector. That's called the index ellipse. And the surface where it intersects the index at the ellipsoid is the index ellipse. All right. Then in the directions of the normal mode, say dA and dB now, we have where the index ellipse intersects the index ellipsoid. In this direction, we have the index of refraction for the normal mode B and the index of refraction for the normal mode A. That's what you need. You need the indices of refraction so you can find the propagation constants, and you need the direction of polarization, right? So then there's dB and dA. You can find these through this graphical construction that we went through, or you can solve directly from Maxwell's equations, assuming plane wave solutions, constructing a wave equation, and recasting that as a eigenvalue problem. All right?
Only exist on the surface of the ellipse with the index N1 and N2, or is it a volume?
The ellipsoid?
I mean, like near NA and N1 and N2.
Yeah.
So does it only exist on the surface of the ellipsoid, or is it a volume value where we have?
No, this is the surface. These are existing on the surface of the index ellipse. Yeah, they're on the surface. The intersection of this plane that's orthogonal to U with the index ellipsoid gives you an index ellipse, and at the intersection where the half minor axis, major axis of that index ellipse is where the normal mode index of refraction are. Okay, so uniaxial crystals. So I guess a better presentation of this would have been to have sort of the general dispersion relation first, because then we see that there are two sheets involved in solving that general dispersion relation. And those two sheets intersect either at some point, well, 2 points, right? Either 2 points because it's symmetrically opposite. So either at a point or 2 points, you draw a line through it, or at 4 different points and you draw 2 lines through it. So it's uniaxial or biaxial media. And each of those lines that you draw are called the optic axis. And along the optic axis, you get ordinary index of refraction. Okay, so let's say we have some medium with the optic axis in the vertical direction here. This is an anisotropic medium, and we're traveling in a direction that makes an angle theta with respect to the optic axis. All right? Okay, so we can parameterize the index ellipsoid in this case, or the index ellipse like this. This is a parameterization of an ellipse. And this is the index ellipse, right? And here we have the angle theta. Here's the optic axis where we have n naught. Orthogonal to that, we have the extraordinary index of refraction. All right, so as you change theta, or the direction of propagation with respect to the optic axis, you can pick up the index of refraction by finding so it's the same thing as this, right? Look here. This is an index ellipse, right? And what we do with the index ellipse is we find the major axis, or the half major axis, the half minor axis, and we find the index of refraction there, right? So here, it's the same thing. We have this index ellipse, and the intersection of that index ellipse, or the perimeter of it, is then the index of refraction. So as we travel, say this is the optic axis in this direction. As the plane wave travels in different directions, it sees different indices, and therefore it travels at different phase velocity. There's a lot of things you can do with that engineering with it, right? You can have some kind of modulator that changes the propagation velocity. Of course, you have to then change the direction back or so forth, right? You can start to be imaginative. All right, so the normal modes have refractors NB, which is N naught, and NA, which is N of theta. The first mode is called the ordinary wave, and it has index N naught regardless of theta. It's an ordinary wave because nothing special. E cross H gives you the direction of propagation. And of course, we know that D crossed with B always gives you K, dBK, right? D crossed with B always gives you K, but E crossed with H gives you K only in isotropic media, or in this case, the ordinary wave. It's just an ordinary plane wave, right? Same E cross H gives you, or E cross H gives you the direction of propagation, right? The extraordinary wave, that one's different. It's extraordinary. It has a different refraction index that depends on the angle of propagation, and we no longer have E cross H gives you the direction of K, right? Now, but for sure, D and H and K are orthogonal. D cross H gives you the direction of propagation, but E cross H now is in a different direction than K. And we know that power flow is E cross H, right? E cross H conjugate, 1/2 real part E cross H conjugate. And we know that phase delay is in the direction of K. So no longer is phase delay and the direction of power flow parallel. And that's what we'll get into today. It's interesting. All right, so you can use the standard relationships here to find all this. K cross H. So this is Ampère's law, Faraday's law, written for plane waves. We have the direction of propagation, or sorry, the power density there, pointing vector. And from all of these relationships, we can derive the following. H or B are always in a plane orthogonal to a plane, the gray plane, containing D, E, K, and S. All right, for magnetically isotropic media. So D, E, K, S are all in plane. All right. E crossed with, okay, so here we see E crossed with H will give us power, right? 1/2 part of E cross H is always power. So E crossed with H will give us power flow, S, and D crossed with B always gives you K. But if D and E are not aligned, because H and B are, then K and S will not be aligned. So you can start to tailor the flow of power independently from the direction of travel or the direction of phase delay. And this paper that I pointed you guys to read, if you're excited about it, is a good one to start. All right. Okay, now we get into the general case. We have the dispersion relation we can derive directly from Maxwell's equations. Here we have plane wave solutions that we're assuming we're in infinite isotropic and isotropic media, plane waves traveling in these media. So we can derive a wave equation for the plane wave assumption. And if we also assume that we have epsilon as a permittivity tensor now, rather than a scalar, then this equation can be written like this, all right? You just expand it out, right? You do the two cross products with K, and then you expand out this product of epsilon dotted with E. All right, then you have this tensor, or sorry, this matrix equation, yeah? This is some matrix multiplied by an electric field equal to 0, and we know that our electric field is not 0. So for non-trivial solutions, this coefficient matrix, the determinant of it has to be 0, right? So we take this matrix, we take its determinant and set it equal to 0. The straight bars indicate determinant, all right? Okay, good. Now, if you do that, you'll find this thing called the normal surface in K-space. So taking the determinant of this and setting it equal to 0, you derive a functional form of this form, a function of this form, omega as a function of K, aka dispersion, right? Omega as a function of 3 independent directions now, though, K1, K2, and K3. So we can plot that dispersion relation, K1, okay, so Kx, Ky, and Kz, Kx, Ky, Kz, or K1, K2, K3, right? So in K space, you can plot this surface, omega, this is omega, the surface, as a function of K1, K2, and K3. And if you do this determinant, you'll find that there are 2 sheets. So let's look at that. There are 2 sheets, right? The K surface is a centrosymmetric surface comprising 2 sheets, each corresponding to its solution, normal mode, right? This must be some kind of quadratic dispersion relation. You can probably write it in that form, right? You solve this, you end up separating. So the determinant of this you can write as the product of two terms is equal to 0. So that either one term is 0, you get a surface, or another term is 0, you get a surface, right? Yeah.
What is omega in the determinant? In case you.
No, omega is not here, right? So you just call this thing omega when you set this determinant equal to 0, but omega is embedded in K naught. So you can write it in that form, right? Okay, so you get 2 solutions. You get something. Let's see here. Is this the right pencil? Wait. Oh my goodness. Oh. Okay, so my Apple Pencil's dead. All right, so you get a product. You get one term multiplied by another term is equal to 0, one term equaling 0. So you have a product of A times B equal to 0, right? Either A is 0 or B is 0. If you said A equal to 0, you get some surface or a sheet. If you said B equal to 0, you get another sheet. Now those two intersect at some point, right? So here they intersect at the optic axes. So this is a biaxial medium, right? It has one axis going through this. See these 2 sheets. So here's one here, this one, and then there's one here that goes this way. And those 2 surfaces, they intersect at some point, meaning they have the same index of refraction at that point, right? That is the optic axis. There's another point of intersection. There's another optic axis, is biaxial media. I'll show you an example in a second. At the top, there's an animation showing how these 2 surfaces intersect. There's a darker ellipsoid and a lighter ellipsoid. Those are the 2 solutions to this dispersion equation. And you can see that they have the same value. They intersect only at 4 points. And it's centrosymmetric, meaning that one of those points is diametrically opposing from the origin. You could draw a line through it, right? You can draw a line through this other 2 points and you get 2 optic axes, biaxial media. All right. So we call these normal surfaces, right? The intersection of the direction of propagation with the normal surface determines the vector K. So, okay, so now that we're drawing this in K space, right? Before, we were drawing these surfaces in N1, N2, N3, right? We were drawing it in the coordinate system where we drew the index ellipsoid. So the ellipsoid represented the index of refraction in the different directions, right? X1, X2, X3. And therefore, each point on that surface gave you an index of refraction. But now we're drawing these in K space, Kx, Ky, Kz. It's very related, right? There's some constants. I think N over C is, it's very related, right? So we're drawing in K space though. So all the points of intersection, these points on these surfaces represent K vectors, all right? Okay, so in the easiest case, when all three indices of refraction are the same, we end up with a isotropic medium, means there's two spheres, right? And those two spheres are concentric and overlapping. So we only get one index of refraction, n, right? All right. And yes.
These are wave numbers are different waves that's propagate in that media. So when they intersect, we have that. I don't know, it's just a wave number of different waves.
The different directions, the wave number, remember the medium's anisotropic now. So the phase velocity depends on the direction of travel.
Different direction, yeah.
Or sorry, yeah, direction of travel in this case, the way these are plotted.
Why do we need them?
What's that?
Why do we need them to determine the axis, optical axis, or what?
Yeah. You'll see soon. By having these surfaces drawn like this, we're able to define easily the direction of power flow and the direction of phase delay or the direction of wave travel. Because, so look here, for example, we know that the intersection of the point or vector drawn from the origin to the K surface, right, gives you the wave vector K. So the vector position from the origin to the surface gives you the K vector and the magnitude of K and the direction, right? Now, the vector which is orthogonal to the surface gives you the direction of power flow. So if it's elliptical, if it's circular, right? So here, the ordinary, here's the ordinary sheet, right? The one associated with the ordinary mode. So it's a circle. So that means K is in the, so if you draw a vector from the origin to the intersection of the circle, then that gives you K, right? And the direction of propagation. And power flow is normal to that circle, which is parallel to K, yeah? If it's an ellipse, which is the case for the extraordinary mode, then, for example, if you look here, or somewhere over here, I need to draw this because, let me see if this pencil has anything. We might have it on the next slide. Here's a quick preview of it, all right? Okay, here's a quick preview. So here's a K surface, right? Here's a vector drawn from the origin to the K surface. That gives you the direction by nature of it being drawn in the K space. And the length of that vector gives you the magnitude of K. The vector which is normal to that K surface tells you the direction of power flow. So you can see that these two aren't parallel anymore. For an isotropic medium, where you have the ordinary mode, these two are parallel because it's a circle, right? But here, when you have an ellipse, then these two things decouple. Okay, let's see. So let's read these. The intersection of the direction of propagation with the normal surface determines the vector K, whose magnitude is K equal to N omega over C. So this K and this N surface are very related, right? It's just a constant omega over C. Provides the refractive index N. There are two intersections corresponding to the two normal modes associated with each direction. All right. The K surface is a centrosymmetric surface comprising two sheets, each corresponding to a solution. As we said, it can be shown that the K surface intersects each of the principal planes in an ellipse and a circle. So, okay, what they're saying there is we always get an ellipse and a circle in general, right? For biaxial crystals, the two sheets meet at 4 points, defining two optic axes. As we said, here's a biaxial medium. We have this surface intersects there, and there's some point on the opposite side where it intersects. And then if you were to continue this surface, this is only showing like an octant, then there'd be another intersection point, right? For uniaxial crystals, the two sheets become a sphere and an ellipsoid of revolution that meet at only 2 points. For example, like this one, right? Or this one. Or no, this is biaxial, right? because it meets here. So, okay, biaxial. We have a circle. This one is a circle, and then we have an ellipse. It's always a circle and ellipse, right? So if you have intersection point here, 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 and here, those are 4 intersection points, you get 2 axes. Those are the optical axes. You get normal modes, ordinary modes in that direction. Here is a uniaxial medium. We have a circle and an ellipse. They only meet at these 2 points. That defines the optical axis.
Triaxial, you have 3D ellipse.
No. Triaxial not possible with this 3 dimensions.
You can have a circle, you can have a squash ellipse that intersects at 8 points. Along
I'd have to think about that. I don't think it's possible though. Okay, we'll think about it. Okay, single optical axis. And we make that the z-axis in general. In the isotropic case, the 2 sheets degenerate into a single sphere. All right, good. So let's look at that. So let's take a look at it. If we solve the dispersion relation, then we end up deriving an expression like this, right? So we have this, if you can rewrite the determinant like that. And then we solve for okay, first, the intersection of a direction u with these 2 sheets, with the index ellipsoid, the K surfaces, they give you this kind of equation here. So this is the solution to the dispersion equation for a given direction u. And the intersection of the direction u with the K surface corresponds to wave number K that satisfies this equation. So someone has solved this for you, and I've uploaded that reference for you to read on the website. But they've solved that dispersion relation for you for a given direction u, and it's in this form. And you can write it like that. So it's a 4th order in K or 2nd order in K squared, this equation here that you have to solve. That's what gives you these 2 sheets. So given the direction of propagation u within the anisotropic medium and the 3 principal refractive indices N1, N2, and N3, so you're given these 3 principal indices and a direction of propagation, one can numerically solve the equation above and obtain the 4 solutions K equal to plus or minus Ka and K equal to plus or minus Kb. So there's an A mode and a B mode, of which the 2 positive values are meaningful as the 2 negative values represent a reverse direction of propagation. So either travel plus K that way or minus K in that direction, right? The refractive indices of the normal modes are then, okay, so you can divide Kb by K naught or Ka by K naught, all right? I did that numerically here, tried to think of a quick example. Mica, for example, is a biaxial crystal. It's a material with principal refractive indices N1, N2, and N3, shown here. If a plane wave is traveling along the direction u, so this direction u hat, 1, 1, 1 direction, right? Determine the normal mode wave numbers and indices of refraction. I wrote some quick code here in MATLAB and tried to solve that dispersion equation. And I've included here. So what we find is 1.56 and 1.58. Okay, very good. So you can
a relation between, let's say, refractive indices and the Bragg numbers or the crystal.
Okay. The Bragg number. Yeah, I'm sure. Okay, so then you're talking about periodic media, right? If you're talking about Bragg, you need some kind of reflection. And here it's anisotropic, but it's infinite with no discontinuities. So we'll get to that, I think, coming up here. So let's read the dispersion diagram, right? If we plot these K surfaces, the phase velocity Vp is equal to omega over K in the direction u is inversely proportional to the distance from the origin. Okay, so what they're saying here is, if you have the phase velocity, we know is equal to omega over K, right? So then if we can read K from here to here by finding the length of the vector, which intersects the K surface drawn from the origin, we get K. So that means the phase velocity is inversely proportional to that distance, the radius of the ellipsoidal sphere, right? Okay, so what does that mean? If the sphere is very big, right? If the sphere has a large radius, what does that mean for the velocity of propagation? Very good. And if the sphere is very small, then it travels very fast, right? The group velocity is the vector. Okay, so you take this gradient in K space of the normal surface, right? Of the dispersion surface, these K surfaces, the gradient in K space of the dispersion plot. Now, what do we know about gradient vectors, right? Think about equiphase surfaces. If we have our equipotential contours, right? What direction does the gradient point? Or you can think of level curves of a mountain, right? So you have, what direction does the gradient point in? Maximum rate of increase, right? So, and therefore, by nature, it's also orthogonal to the direction of constant isocline or so forth, right? Or equipotential. So these vectors, gradient vectors in the K space are orthogonal to surfaces of equal K. And that's what these K surfaces are. They're surfaces of constant K. So then this vector is orthogonal to those. If you take the gradients of that surface in K space, then it's a vector which is orthogonal to the K surface, right? Okay, so the group velocity, okay. Since the gradient is normal to the K surface, the group velocity vector is normal to the K surface. Thus, rays travel along directions normal to the K surface. All right, so we have to disambiguate a ray from a direction of propagation or phase delay, right? When they say rays here, they mean the direction of power, right? The direction that the power flow is flowing. So we can see a ray here and it has wavefronts which are orthogonal to it in this case. For an ordinary mode, we have the K surface, we have K and S are parallel. And so in the direction of the ray is also in that direction, right? So rays travel along directions normal to the K surface. The wavefronts are perpendicular to the wave vector K. The wavefronts are perpendicular to the wave vector K. That's what the wave vector K means. It's the phase delay in some direction, right? Thus, the wavefront normal are parallel to K. Okay, so if you have a wavefront, a plane wave that is constant phase cutting this entire room like this, there's a vector, the K vector is orthogonal to that plane. And what they're saying here is that that's K and the wavefront normal. That's okay, so that's kind of known, right? The complex pointing vector is normal to the K surface. Consequently, S is also parallel to the group velocity vector. So that's also true. S is in the direction of group velocity. Okay, so the rays travel in the direction parallel to S. So these are all a bunch of facts, right, to allow you to understand it. So in ordinary mode, we have the phase velocity, or sorry, the group velocity, the energy velocity. S and K are all parallel, indicating rays are parallel to wave vectors K and energy flows in the same direction. When we have an extraordinary mode, the group velocity, the power flow, and the K vector are not parallel, indicating rays and direction of energy transport are not orthogonal to the wavefronts. The rays then have the extraordinary property of traveling at an oblique angle to their wavefronts because the K vector is this way. So the wavefronts are orthogonal to this K vector, but the ray, which is in the direction of power flow, is traveling in a different direction. S and K are not parallel. But the wavefronts are still orthogonal to K, but the ray is traveling in a different direction. So these wavefronts are not orthogonal to the ray. So it looks kind of funny. I think I have an animation in here. Let me show you that really quick. Oh, no animation. Terrible. Okay.
Does it curve like the S, like if we're thinking of contours in the extraordinary space, as the ellipsoid is increasing in radius, S is curving from the origin. Sort of.
Yeah, I mean, as you travel in different directions. So K changes direction, right? So if I start changing direction of propagation, my power starts to flow in different directions.
So we'll go counterclockwise.
Yeah. So you can probably, if you have a K surface, then you can start to plot the deviation angle between the ray and K, right? Yeah, very good. So let's look at a quick example. This one will kind of bring everything together for you. A uniaxial crystal. In uniaxial crystals, the equation of the K surface simplifies to this. So this is a case where you can actually solve that dispersion equation, this determinant of the dispersion equation equal to 0. If you solve that for a uniaxial case, then you end up with this, which you can see separates into two terms equal to 0. One of these is one sheet, and one of these is the other sheet. One of these is a circle or a sphere, and one of these is an ellipse or an ellipsoid, right? So the first one is a sphere of radius k equal to n naught k naught, because it's the ordinary mode, right? N naught. The second term equal to 0. So to satisfy this equation, either this term equals 0 or that one equals to 0. This term is an ellipse, right? The equation of an ellipsoid of revolution with this kind of equation. All right? Yeah? Questions? All right. Okay. So I'll give you guys a couple of minutes at the end to ask questions to make sure. Because, okay, this is a new topic, right? What's happening here is we're getting bombarded with definitions and new things we haven't seen before. And there's a lot of terms that we haven't been familiar with. So to keep up the discussion, we need to learn these terms and keep them in the back of our mind. We're trying to connect them all as we're learning this new stuff, right? And it probably can get difficult if you can't speak the language to understand what I'm saying. So what I want to make sure is that if you have questions, you need to ask them, because you might, if you got lost a few slides ago, then bring that up, right? And I'm sure it's because of the terms, a lot of new terms, right? Okay. Okay, K1's in and out of the board, right? K1's in and out of the board, K2 is this way, K3 is that way. This is the cross section of, for a uniaxial crystal, we end up with a circle, which is concentric to an ellipsoid. It fits right inside of it, right? Only in this case, with this circle and the ellipsoid intersect at only these 2 points. If this radius of this circle is any bigger than exactly tangent to this ellipsoid, then you're going to get 4 intersection points, right? Medium becomes biaxial. So here we saw this before, right? We have some optical axis where these two intersect. We travel at some angle, theta. We can calculate the ordinary index of refraction for the ordinary mode, and by intersecting with the circle, and the extraordinary index of refraction, if you will, which is in this direction. If you go all the way to this direction, you get the extraordinary index of refraction. But in between, you get something which is sort of a parameterization based on the ellipse, interpolation between the two, right? So in this direction, when you get this other index, n of theta. All right? Those are your two normal modes. That's good. All right, so the ordinary mode, as we've seen before, we have h in some direction orthogonal to the plane containing E, D, K, and S. But this is ordinary. E crossed with H gives you S, and it gives you K, right? Because it's a circle. So we have this kind of relationship. The wavefronts are orthogonal to the ray, because K is parallel to S, and the direction of the ray is the direction of S, and the direction of travel is K. Here we have the extraordinary mode, where H is orthogonal still, but E crossed with H gives you K, and D crossed with B, which is the same direction as H because it's magnetically isotropic, gives you S. No, said that backwards. Holy moly. E crossed with H gives you S, right, the ray. But D crossed with H gives you K. All right, good.
We're not magnetically isotropic, and we have a B vector as well. Do we have a hysteresis in power? One is power loss of the magnetic tension.
Well, then you probably have to repeat this analysis with the permeability tensor, mu, and combining the two is probably a complicated thing to visualize. But yeah, it's possible, right? Just repeat this analysis and incorporate the impermeability tensor. It's probably a much more difficult dispersion surface to solve. Okay, so we see K and S are not in the same direction. The wavefronts now are not orthogonal to the ray. And here we have a diagram showing the wavefronts again. These are now not orthogonal to S. They're orthogonal to K. We have D crossed with B gives us K, and E crossed with H gives us S. So these two things are traveling in different directions. Good. Okay, so that does it for what we're going to talk about for anisotropic media. Read the handout that's on the website if you want to get more information on this, or come to my office hours and we can talk about more, yeah? So what I suggest is go back through and try to pick up the terms and study it a little bit. And once you understand the terms, then you can start to look at the way that these dispersion surfaces, the dispersion equation, the case surfaces start to evolve into the different cases, and how to pick out the normal modes, and then what happens when you have propagation in these directions, right? All right, let's talk about periodic media briefly. We now consider infinite periodic media. For example, consider the infinite media constructed from alternating slabs of permittivity epsilon 1 and epsilon 2. So now still infinite, unbounded media, but it's now periodic. We have epsilon 1, then epsilon 2. Epsilon 1, then epsilon 2. The period here is d, and the wave is traveling in the z direction, for example. Since the permittivity varies periodically, the wave number k, which is equal to omega square root of mu epsilon, and epsilon's periodic, then the wave number k also varies periodically, right? So the wave number here is say epsilon 1 is greater than epsilon 2. The wave number here is greater than less, greater than less, greater than less. So it's varying periodically as well. We will solve the wave equation in this periodic media. We have del squared psi plus k squared psi, but we know k now is periodic, for a periodic wave number, p of x, where p is a periodic function. We can also evaluate the expression at one period away. So it's del squared psi x plus d. So we're going to evaluate it at, oh, that's not good. This should be z, right? Because the way I've drawn this medium, turn this pencil. So imagine this is x. Why is my pencil not charging? Okay. That's kind of concerning. All right. So, okay, so yeah, this should be z, yeah? It's periodic in the z direction. But let's actually assume that this figure is labeled incorrectly. So it's periodic in the z direction, or x direction rather. So the mathematics is less to change, right? So assuming it's periodic in the x direction, del squared psi x plus d, y, and z plus p of x plus d psi of x plus d, y, and z is equal to 0, right? Since the wave number is periodic with period d, we know that p of x plus d is equal to p of x by definition of periodicity, yeah? All right. Also, the second partial with respect to x can be written in the following way. We have partial squared psi of x plus d over partial x plus d squared. Well, that's nothing but partial squared of psi of x plus d over partial x, because it's still just a differential displacement here, right? Therefore, we can say that del squared, if you expand this in terms of the partials of x, the second partial of x, second partial of y, second partial of d, or z rather, then del squared of psi x plus d plus p of x psi of x plus d equals 0. What are we saying here? This is the same equation, right? Yeah, we're just being more explicit about this equation and this equation. So this one is the same as this one because p of x plus d is equal to p of x, and we know that this we can write this Laplacian in this way, right? So Laplacians are the same. All right, so that means that both psi of x plus d, y, and z and psi of x, y, and z are solutions to the wave equation. Does everybody see that? So here, look, for sure, in this red equation here, that psi of x, y, and z is the solution to that differential equation, right? With p of x. I can write this one period away, and I get a different differential equation, right? This coefficient is different, and this Laplacian might be different, right? But what we're showing is, because it's periodic, this wave equation, we can reduce it to this wave equation, right? The solution to this one is psi of x plus d, y, and z. But it's the same exact equation as this one. So both of these solutions, psi of x, y, and z, and psi of x plus d, y, and z are solutions to the wave equation. All right?
Fall within the Fourier general. We have a spatial Fourier Fourier general, so just a simple operation.
Maybe you can solve it in the Fourier domain because it's periodic. Yeah, might be able to do that. Yeah. Yes.
Can we say the same for a media which does not have two permittivities, but one permittivity decreasing uniform?
One permittivity increasing uniformly. So it's a linearly increasing permittivity? No, because that's not periodic, right? The only way that you get the same solution at one period away as you do at, say, some given point is if the permittivity is periodic, if the wave number is periodic. If it's linearly increasing, then you can solve the wave equation for that case, right? But it won't get the same conclusion as we do in this case. It's not the same.
This set of helpful in propagation of the traveling.
Yeah, so there are things called leaky wave antennas, for example. You can model those as periodic surfaces. And in a periodic surface, you can have a wave traveling along a surface which is periodically modulated, if you will. And you can generate modes that leave the surface. Surface wave can convert to a propagating wave or partially. Or you can have media, which you make as like a metamaterial, which is a big crystal, for example, that has periodic inclusions, and you can analyze it. What we're going to derive is a very, very, very important consequence in electromagnetic theory called the Floquets theorem. All right, and that also you can, if you have unit cell analysis, for example, if you do a simulation in CST or HFSS, and you put periodic boundaries around your simulation domain, then that is a Floquets theorem problem. It's a periodic, infinite periodic medium.
So if we take the limit S2 goes to 0, do we have one effective epsilon, or do we have to integrate two different epsilons?
It depends on how that limit is taken, right? If the limit is taken such that epsilon 2 shrinks to nothing and epsilon 1 is there, then of course it becomes just homogeneous medium, right? Okay, so let's derive the Floquets theorem. If U of x and V of x are two linearly independent solutions to the wave equation, so we have a second order differential equation. It has two linearly independent solutions. We're going to call those U of x and V of x. With periodic wave number, then so is U of x plus d and V of x plus d, because we said that the solutions to the wave equation one period away are also solutions in the cell of interest, right? Based on this, we said that if psi of x, y, z is a solution, so is psi of x plus dy at z. It's also a solution because of the way that the wave equations are the same, right? Same wave number. Same coefficient here, same differential operator. This is the solution to this differential equation. The only thing characterizing this differential equation is the Laplacian and this coefficient here. They're the same here, Laplacian and coefficient. So this is a solution to that wave equation. So is this. Okay, so if the solution to the first differential equation, the first red one here, if we say that the solution to this equation is U of x and V of x because we have two linearly independent solutions, then that means that U of x plus d and V of x plus d are also solutions, right? Very good. However, there can only be two linearly independent solutions to a second order wave equation. They're both modeling the same medium, right? There can only be two linearly independent solutions. So two of these must be linearly dependent on the other two, right? Thus, U of x plus d and V of x plus d must be linear combinations of U of x and V of x. We will see that this linear combination is a complex constant in the form of a complex exponential. Nonetheless, let's derive it. We're saying that U of x plus d and V of x plus d have to be linear combinations of U of x and V of x. So let's say U of x plus d is some coefficient a times U of x plus some coefficient b times V of x. And let's say that V of x plus d is some coefficient c times U of x plus d times V of x. Yeah? Okay, A, B, C, and D can be suitably chosen for actually periodic structures, for example. Okay, so A equals to D equals to 1. So we'll come back to that, all right? All right, so let's assume a solution to the 1D wave equation now. We're just ignoring Y and Z. Let's assume the solution to the wave equation in the form of psi of x. We can always write a solution, a general solution to our wave equation as a weighted combination of our two linearly independent solutions, right? So this is one solution, this is another. Taking weighted combinations of these two solutions is also a solution to just the one second order partial differential equation. All right, so we have these two expressions, right? All right, if psi of x is to represent wave propagation down the structure, for example, then psi of x plus d should equal to e to the minus j kxd into psi of x. So, okay, this is saying that if we have waves traveling down some direction, then their phase delay should be of this form in rectangular coordinates, right? It should be this solution, but then we have e to the minus j kxd amount of phase delay, since we're only traveling in one direction, at this point, d, x plus d. All right, all right. Okay, so that's all the stuff we need. Now we can start adding these kind of facts together. So I have x plus d now is equal to m of u of x plus d plus n v of x plus d. Weighted combinations of the two solutions to the x plus d wave equation. Very nice. But we know what u of x plus d is. It's a u of x plus b v of x. So let's plug that in. And we know what v of x plus d is. We'll plug that in. And if we do the multiplication, we end up with ma plus ncu plus mb plus ndv, right? All right. Let's see if we can determine the coefficients m and n, these two coefficients m and n, that satisfy this kind of relationship. We want there to be some phase delay down the structure based on its distance of travel. Okay, so let's take this psi of x plus d, which we now have written in this form. Let's put that on the left side. We have e to the minus j kxd, and then psi of x we know is m u of x plus n v of x, yeah? All right, good. So now we just need to factor out the u of x's and combine the coefficients, right? Factor out the coefficients and, or combine all the coefficients. We end up with this expression here, which is some coefficient multiplied by u plus another coefficient multiplied by v equals to 0. Since u and v are linearly independent, then both the coefficients have to be 0. Because these are linearly independent, you cannot combine them in any way to get 0, right? Think of them as being orthogonal. So that means that this coefficient has to be 0, and so does this coefficient. If both these terms summed together have to be equal to 0. Okay, good. All right, I've repeated the equation at the top. Both those terms have to be 0, right? So since both of these are needing to be 0, we can write them in a matrix form like this. Now we have something we can solve, right? M and n are not 0 because what is m and n? M and n are the coefficients of our wave solution. We don't want it to be 0 because if these were both 0, then our two solutions weighted together by m and n gives us our wave or our solution. We don't want m and n to be 0. So that means this coefficient matrix must be 0, or the determinant of it, rather, has to be set equal to 0, right? So we set the determinant of that equal to 0, and we end up with, we solve for this, e to the minus j kxd. We end up with this expression here, all right? Very nice. Let's consider some cases. We're still free to choose A, B, C, and D, right? We still need those numbers. So if A equals to D equals to 1, then e to the minus j kxd is equal to 1, right? Okay, so e to the minus j kxd is equal to 1. Then we can write this as cosine minus j sine kxd. And what we find here is kx needs to be 2 pi n over d. All right, let's understand this. So when kx is, we need this to be 1, right? So let's first start with n equals to 0. We end up with kx equal to 0. Kx equal to 0 gives us 0 for this term, gives us 1 for that term. That satisfies that equation, yeah? Okay. What about when when n equals to 1? We get 2 pi over d, right? So if we go here, cosine of 2 pi over d multiplied by d is cosine of 2 pi. That gives you 1. And we get sine of 2 pi, which goes to 0, right? For all of these, you're going to have this expression, right? Because this has to equal to plus 1, which is a real number, this sine term has to always be 0. Yeah. Okay, so that's awesome. That means we found the wave number for periodic media that satisfies a periodic wave equation. So thus, if kx is 2 pi n over d, meaning that there's a bunch of different kx now. This goes out to infinity in general, right? So there are a bunch of different wave numbers that are generated due to the periodicity of the medium. Kx equal to 2 pi n over d, then now we can say our solution, psi of x plus d is equal to e to the minus j kx d times psi of x. That was the solution we were searching for. There are also, okay, so, but then we know what kx is now, right? Kx is 2 pi, so it's kx not plus 2 pi n over d. Okay. This is the Floquets theorem here. But I think I expound upon that on the next slide. There are also complex solutions to this equation here, which gives you, that involves a sign, right? But we're not going to consider those right now. So here's Floquets theorem. This is something you should remember from this lecture if you don't remember anything else. All right. Electromagnetic fields in one unit cell differ from the fields in an adjacent unit cell by only a complex constant representing the phase delay and attenuation of the propagating waves. All right. If I have media and I'm traveling through some periodic medium, then if I have a given unit cell in an infinite periodic medium, the only difference between the electromagnetic fields in that unit cell and the neighboring unit cell is a complex constant, meaning that there's some phase delay between the two cells and there's some amplitude decay, maybe, right? It's alpha plus j beta. But the electromagnetic field itself, the structure of the field itself, will be the same, except it'll have a phase offset. Think about modes in a waveguide, TE10. This is not periodic medium. But if I have a mode in a waveguide, then the cross-sectional field distribution is the same, anywhere down the waveguide, right? The only thing that changes is the e to the minus jkz, for example. It changes phase. Well, this has the same exact field distribution in every unit cell in the periodic medium, except that there could be a phase delay, complex constant phase delay, because of the constant distance between the unit cells. That changes the phase and amplitude. All right, good. So this is the Floquets theorem. The electric field for a structure that is actually periodic and traveling along the z direction. So the electric field in the neighboring unit cell at x plus d is exactly the same as the electric field in the unit cell of interest, x, y, and z. The electric field is the exact same. It has a different phase though. You multiply it by a complex constant. So it could have a different phase and it could be an amplitude as well that's different. But the field vectors are the same. There's the same direction and so forth, right? The vector field is the same, except it is multiplied by a complex constant. So it could change direction if the phase is 180 degrees, right? The difference in phase between one cell and the next. And the vectors could be reduced, but they're in the same direction. Good. That is the crutch of unit cell analysis in simulation software. So the
Fourier series, the step in between two indexes, that would be what the Fourier series is just that wave.
The Fourier series for a square wave. Okay, so the Fourier series of a square wave, the square represents the permittivity. Those coefficients are related to the spatial harmonics. Okay, so we got the spatial harmonic wave numbers here. But to get the amplitudes, it involves a series expansion, right? In terms of these Floquet plane waves, which bears a resemblance to a Fourier series. I think we get into that right here. So the electromagnetic field at any point in the unit cell will take on the same value at a similar point in an adjacent cell, except for a complex constant e to the minus jkxd, where kx is referred to as the block wave number. All right. The most general solution that obeys the Floquets theorem, psi of x is our solution, right? Is some periodic function q of x times e to the minus jkxx, right? This is the most general solution to the Floquets theorem. So q of x is periodic, right? Let's see what that is. So if we take our solution psi of x plus d, and we evaluate our general solution, let's see if this solution satisfies the Floquets theorem. So that it has to satisfy the Floquets theorem, right? The Floquets theorem was derived from the wave equation, which is derived from Maxwell's equations, assuming periodic media, which made the wave number periodic, which is one of the coefficients in the wave equation, right? We derived this expression by solving that wave equation in periodic media called the Floquet theorem. And this expression here we're claiming satisfies that Floquet theorem. Let's find out. Psi of x plus d. If this is psi of x, then psi of x plus d is q of x plus d, e to the minus jk x plus d. Replace x with x plus d. All right. Q of x is periodic with period d, so q of x plus d is equal to q of x. And we can separate this exponential into e to the minus jkxd and e to the minus jkxx. But we know that q of x, e to the minus jkxx, is nothing but psi of x. So we end up with e to the minus jkxd times psi of x, which shows that psi of x plus d is equal to this complex constant multiplied by psi of x. This could represent the x component of the electric field, psi. It's a scalar function, so it could be one of the components of this Floquet expression, right? All right, good. So since we know that q of x is periodic, we can represent q of x in terms of a Fourier series. So we can also write psi of x as q of x e to the minus jkxx, but we can say that that's e to the minus jkxx and expand q of x into a Fourier series, right? Fourier series is n equal to minus infinity to plus infinity, some complex coefficient an, e to the minus j 2 pi over d times n times x. Fourier series. That's directly Fourier series. But we recognize 2 pi n over d as our kxn, right? We're going to call it kxn, in other words. So if we let, So here, look. We should have said this first. If we let kxn equal to kx plus 2 pi n over d, because we have a kx out front, we have a 2 pi n over d. If we combine this exponential with that one, this kx doesn't depend on n, so it just becomes kx. And then we have this 2 pi n over d is the other component of kxn. Then we can write it like this. What does this say? This says that our electric field component, or scalar field, psi of x, can be written as a superposition of plane waves. This is a complex coefficient. This is an exponential function. And we're summing these up. So they're plane waves. It's a plane wave expansion. We're summing a bunch of plane waves. Each of those plane waves have a different wave number. In fact, those different wave numbers have this kind of relationship, some constant plus 2 pi n over t. So we're increasing by 2 pi n over d each of the modes that we're using, each of these plane waves. And then they have these coefficients an. All right? So I'm taking a periodic electromagnetic wave or field, psi of x, and I'm expanding it in terms of what are called spatial harmonics. All right, so our field solution psi of x can be expanded or represented in terms of spatial harmonics or axially traveling plane waves with harmonic wave numbers kxn. Very cool theorem. What do these spatial harmonics look like? Okay, so let's take a look. If we let kxn equal to kx plus 2 pi n over d, our field solution psi of x can be expanded in terms of spatial harmonics or axially traveling plane waves with harmonic wave numbers kxn, like this. So here's our electric field. We have the direction, the axial direction of periodicity. We have this wave number lambda n, depends on n. If we consider different harmonics in that series expansion, this wave number changes, right? Period. And we add up all these plane waves to synthesize by superpositioning of all of them, whatever periodic field distribution we want. It's like a Fourier series. You add up a bunch of sine waves, you get whatever periodic function you want. This is a periodic wave function. And we're just adding up a bunch of exponentials to synthesize its periodic distribution, which is in general not representable by a single harmonic, right? You need a bunch of sines and cosines to give you some arbitrary periodic wave function. All right, so let's look at a sinusoidally modulated reactive surface, which is a common thing in leaky wave antennas and so forth. We consider this grounded dielectric substrate. So here's a substrate of permittivity epsilon r, for example. It's got a ground plane under it, and above we have an impedance sheet, which is sinusoidally modulated. So we can see one of these periods going from purple to red is of periodicity d. The substrate has a thickness of h. there's some surface wave, which is the exciting or the fundamental mode, and it radiates, it leaks. As it travels in this direction, it leaks energy at some angle, all right? Okay, if we solve for the dispersion relation for this leaky waveguide, it leads to a complex fundamental. So, okay, there's a way to derive a dispersion relation to find what the wave number of this surface wave is, the fundamental one. We find if you do that, 289.37 minus 5.711, there should be a J here, right? Or no, this is beta minus this alpha. So beta minus J alpha. Okay, so the spatial harmonics are Kx plus 2 pi n over d. So then we can start to plot them, right? I don't know why I didn't put the J here. So it should be, this is beta, this is alpha, but it's in this form, we write it as beta minus J alpha. All right, so we have a bunch of these harmonics. N equal to 0 is the fundamental surface wave, this blue one, right? It's decaying in amplitude because power is leaking from the surface. It's radiating to the far field. So that power that's going off the surface into the far field has to be coming from the surface wave. So it's going to be decaying, right? But because this is a periodic modulation, the electric field in this unit cell is the same as the electric field in this unit cell multiplied by a complex constant, representing the decay and the wave number, right? The phase delay. So all of these other harmonics in the expansion, you can see they start to decay. I plotted them all here, but you need all of these. You add all these together to get what the electric field looks like in a given unit cell, psi of x. We know psi of x plus d is the same as psi of x. So we add up all of these sort of plane wave looking things, right? Just the real part, or these are the coefficients as a function of x. ANs, right? And we know the wave number kxn is this, and we know what kx is by solving the dispersion relation for this structure. These are the parameters we use to solve this dispersion relation. So that's kind of a neat example of where this theory is used.
Angle of the leaky wave, is that determined by the boundary condition?
That's determined by the periodicity. And okay, yeah, it's determined by this wave number, right? Because kxn squared plus ky squared has to equal to k naught squared. And this direction is sort of a kxn and ky. And if you change n, the n equal to minus 1 harmonic is the only one that leaves the surface if your periodicity is a certain value, right? Certain limit. Then it's kind of d that determines what the kxn is of and kx of the or the n equal to minus 1 harmonic. Then you can start to find angles.
So different modes will have different angles.
Yes, but in this case, only the n equal to minus 1 harmonic leaks. Yeah. Okay, good. All right, so you can look at this dispersion diagram if you want. Here's the Bragg thing you were talking about. I'm not going to get into this deep. I think there's another class that I teach in the school called metamaterials that you can take if you want to learn more about these periodic distributions or periodic media dispersion diagrams. But I think I've overloaded you today. So this is the last slide. We'll talk about that if you want. What is this? Okay, we still have a couple minutes. Let me just introduce the next lecture and then we will end. So yeah, those are kind of similar advanced topics, the anisotropic media and periodic media. But that's important stuff too, you know. It's good to see it at this level. And then you can dig into it for your research. All right, so we have studied wave propagation in unbounded media, meaning that there are no discontinuities in permittivity, permeability, or conductivity. So we don't have to worry about reflections, transmissions, or boundary conditions at all yet. We're just studying the properties of waves traveling in these different type of media. We looked at homogeneous media, isotropic media, anisotropic media, and we looked at some periodic media, just introducing it. All right, but now we're going to introduce discontinuities. So the permittivity or the material parameters might change at some point in space, right? We're going to look at infinite interfaces. For example, we're going to learn how to solve these types of problems. All right, so if life isn't so, at least solving electromagnetics problems, it's not so nice where you don't have discontinuities. You didn't need to use boundary conditions, right? But the main part of it, the thing I told you in the beginning of class, the one thing you need to learn, need to remember, need to learn how to apply efficiently and effectively is boundary conditions, because all your problems are going to involve, different scatterers or mode matching, all these different things where boundary conditions become what enable you to solve more complex problems. You need to learn boundary conditions, how to apply them. So here we're going to start with the most basic thing: boundary conditions for discontinuities in infinite half spaces or infinite media. So for example, in the previous lecture, we studied wave propagation in infinite homogeneous media. We now introduce the effects of wave propagation against interfaces between two differing infinite homogeneous media. All right. So for example, here's an interface. On the left half, we have epsilon 2 mu 2. All right. And it's an infinite homogeneous medium in that direction. On the left half side, it's epsilon 1 mu 1, and it's an infinite homogeneous medium in that direction. All right. So what do we have here? Still, my pencil is, I think it's dead for good. It's not taking a charge now. So we have a plane wave called the incident plane wave. In medium 1, which has an electric field and a magnetic field with a superscript I now. Now we have to keep track of which wave is incident, which one's reflected, and which one's transmitted. So there are now multiple waves to consider. There's a reflected plane wave in general. Let's assume that there's one for now. And we assume that the electric field, for the sake of breaking ambiguity, is in the direction of the incident field. So the reflected field maintains the same direction of polarization by convention, right? We could have aligned the magnetic field, but that will lead to a different definition for reflection coefficient. The standard way to do it is to have the electric fields aligned. So we assume there's some incident field, there's some reflected field. The reflected field and the incident field have the electric fields in the same direction, and the transmitted field, some field which is transmitted across the discontinuity, has the electric field also in the same direction. So we align all the electric fields. Then we're going to derive boundary conditions for this assumption, or we're going to use boundary conditions to derive with some coefficients of reflection and transmission for these assumptions. By nature of E cross H giving you the direction of propagation, we're back to isotropic media now. The magnetic field must flip directions for the reflected because it's traveling in a different direction. But the transmitted field has the same magnetic field direction, right?
How should we think of the displacement field of H flipping direction? Like, how does that look when at the boundary where H is going one way and H is going the other?
Okay, so we're at this interface, at the actual interface. All three of these waves are there and they add together. And there will be, by assuming that all three of these exist at the interface and applying the boundary condition, we'll derive coefficients, which might flip this direction of H, or depending on the type of material media on either side. So that coefficient will take care of, all three of these definitions will satisfy the boundary conditions. That's the key.
So just like a standing for that.
Well, you might get a standing wave on the incident side, right? Because you'll have two counter-propagating plane waves. You might get a standing wave there. All right, so that was the introduction to that, all right? Okay, so we'll get back into this next lecture. Remember, next lecture is at 8 a.m. across the hall in Port 1030. And you have your homework due that day as well. And let me know if you have questions, email me. Think about the stuff that we talked about in this lecture. If you have questions, come to my office and we'll talk about it. Yeah, I'll tell you, you won't be tested on the anisotropic. There is a homework on it though, right? But yeah, dig into it, all right? I just want you to, if you go through it and you read the handout that I put there and you start to learn the terms and start to visualize these surfaces, then it should become clear, okay? But let me know if you have any questions. All right, good. Very nice. See you guys. How's it going?
How are you?
Good.
So there's one more question about reflection. Is this something from this chapter that you're starting, or is this just something?
Okay, so you can solve that without what we're going to go through in this lecture because it's just applying the boundary conditions you learned in lecture 1.
So you just assume the reflected and the incident have to add up to give you the field at this.
The total field has to satisfy the boundary condition. So
So
if you have
the
an
field has
incident
to be
and,
0 for tangential.
yeah, tangential E has to be 0. So if you have an incident, field component like this, at the surface you have incident and reflected, you know the direction of the reflected because these two summed together have to give you 0. So the reflected has to be opposite direction.
And you can just solve for the E field and then H just comes from that.
Yes, yeah, that Maxwell's equations, right?
Okay.
Very good.
Yeah.
Oh.
Hey, how's it going? Yeah, come by. When do you, let's see, I have Chopin coming, but you might want to come before him. Or just after him, like 3 maybe? What is the? You should. Yeah. That actually is over angle, right? Stay in far field. So, actually,